Hi everyone, welcome to Banach Spaces webinar. Today we have Chris Gartland from University of Illinois Urbana-Champaign. Chris is a graduate student, or was a graduate student. He just defended his thesis. Congratulations for that, so he just graduated.
Thank you.
And he will be joining Texas A&M this fall as a postdoc. Or hopefully he will be joining, depending on how the situation is going here. And today he's speaking on Lipschitz free spaces over locally compact metric spaces. Go ahead, Chris.
Okay, thank you for the introduction, and thanks for the opportunity to speak in the webinar. So the talk is kind of motivated by two questions. The first question is whether biLipschitz embeddability of metric spaces into Banach spaces with the Radon-Nikodym property is kind of locally determined. So does local embeddability imply global embeddability? And so if you're talking about a locally compact metric space, that's the same thing as asking if embeddability is kind of determined by your compact subsets. And then a second question that's similar in form, but is kind of a disjoint, is the analog of that question for Lipschitz free spaces. So if the Lipschitz free space of a metric space has the RNP for every compact subset, and then is the same true for the whole space. So this talk is going to kind of have two parts to it. The first is going to be background on non-biLipschitz embeddability of metric spaces into RNP spaces using differentiation. And so that's kind of related to the first question, and that's where my motivation for the first question kind of came from. And then the second part of the talk is going to actually have to do with the research that's in the paper, and that's about Lipschitz free spaces. And so I'll talk about the proof of the following theorem, which is essentially a positive answer to question 2 if you just replace RNP with the approximation property or the Schur property. So I guess I should say I don't have answers for either of these questions, question 1 or question 2, but in kind of approaching or the kind of ideas that I was having to go after question 2, it turned out that it was easier if you just replaced RNP with these other properties. And so I'll kind of explain the proof of that just to illustrate the idea. And then hopefully if there's time at the end, I'll describe some very partial progress towards answering question 2. So right, the first part of the talk is going to be completely different than the second part, and you don't need to know one part to understand the other. But I think that this first part of the talk with this non-biLipschitz embeddability using differentiation, I think that for this audience it might be new to a lot of people, and so hopefully people will find it interesting. Actually, before I properly begin the talk, I want to mention something crazy that I think happened. So there was a recent paper posted to the archive by Aliaga, Nu, Pettejean, and Prochaska, and they proved the exact same theorem that I did, but without the locally compact assumption. And I think it was crazy because we were working completely independently, but our papers were posted to the archive just days apart from each other. And it's not like that there was a recent paper that provided the tool that was needed to do this. I think that probably since Colton's 04 paper, this theorem could have been proven, but it wasn't until 16 years later, and then all of a sudden, just days apart, there's 2 papers on similar topic that just popped up. And then I want to mention they also prove the same thing if you replace approximation or Schur property with weak sequential completeness or L1 saturation. All right, now we'll begin the talk properly. So let's start off with the necessary definitions. So a map between metric spaces is Lipschitz if it doesn't increase distances by more than a constant factor. It's biLipschitz or a biLipschitz embedding, or in this talk, probably just embedding. If I just said the word embedding, that'll mean biLipschitz. If it also doesn't decrease distances by more than a constant factor. A Banach space has the Radon-Nikodym property if every Lipschitz map from the reals into your Banach space is differentiable almost everywhere with respect to a Lebesgue measure. So Right. Lebesgue's classical differentiation theorem says that the reals itself has the Radon-Nikodym property. And kind of standard examples and non-examples are any reflexive space has RNP. Separable dual spaces like little L1 also has RNP, but big L1 does not. And so this gliding characteristic function is an example of a Lipschitz function that's nowhere differentiable. And also C0 doesn't. And here's another example of a Lipschitz function that's nowhere differentiable. So there's many other characterizations of RNP, but this is probably the one that's most relevant for the talk. Or it definitely is. All right, so now I'll start talking about a kind of differentiation theory for metric spaces that is going to be useful for proving non-embeddability. So here's the setup. We have a metric space, we have a Banach space, and we have a Lipschitz map from the metric space to the Banach space. And we also have a structure map that takes is a Lipschitz map from the metric space to a finite dimensional Euclidean space. So we're going to refer to this as just a structure map. So the definition is that f is differentiable with respect to the structure map at a point P in the space if there exists a linear map such that the following equality holds. So this little o notation means it's a quantity, so that when you divide by the distance from P to x, it goes to 0 as x goes to P. So you should think of this as saying that that your Lipschitz map f looks like near P. It looks like T composed with psi. Composed with the structure map. And when x is just Rk itself, and your structure map size, the identity map at V has the Radon-Nikodym property, then there's the classical Rademacher's theorem that says that f is differentiable almost everywhere with respect to psi. And right, notice this quantity here. So if psi is the identity map, you're just looking at P minus x, right? So that's just the usual notion of derivative. But if x is not a vector space, if it's just a metric space, then you can't have P minus x. That doesn't make any sense, right? Because you can't do subtraction in a metric space. So the structure map psi, it gives you a way to make sense of what a derivative means in a general metric space. And of course, feel free to interject if you have any questions. All right, so now we'll see how this can play a role in non-embeddability. So fix a structure map from a metric space into some finite dimensional Euclidean space, and fix a Banach space V. Then here's an observation which the application of this differentiation theory to non-embeddability goes back to Schur. But you won't find it presented this way in Schur's paper. So the observation is that if it's true that for every Lipschitz map from your metric space into your Banach space, there's a point P satisfying two conditions. The first is that the function is differentiable with respect to the structure map at the point P. And the second is that P is an accumulation point of the fiber of your structure map. Then there can be no biLipschitz embedding from your metric space into V. So the proof is completely elementary. Oops, let's see. So assume towards a contradiction that you do have a biLipschitz embedding. All right, well then you can choose a point that satisfies both of these properties. So the second condition, since P is an accumulation point of its fiber, you can approach the point along the fiber. And then being differentiable, tells you that this equality holds. But since you're approaching along the fiber, this thing exactly vanishes. So it's just 0. So then this is just little o of the distance between P and x. And well, that's kind of exactly the almost exactly the negation of being biLipschitz. That's a contradiction. biLipschitz would say that say that that quantity is bounded from below by some constant times the distance. It can't be little o. Okay, so this proof was super easy because we've assumed something really strong, right? Saying that every Lipschitz function is differentiable with respect to the structure map, that seems like a wildly strong assumption. And but we'll see actually that it applies to some diverse examples. So we'll talk about two examples of where this applies. So the first, there's a space that people nowadays pretty much generally call Loxo space, even though it first appeared in a paper of Long and Plough. But I guess Long and Plough's construction was, I guess, inspired by a more complicated construction of Loxo, so people kind of attribute it to Loxo. So here's how you construct a space. You start off with just an interval of length 1, that's G0. And then what you do is you replace the middle half of G0 with a diamond. So this middle half gets replaced with this diamond up here. And in general, you can construct a sequence of graphs by replacing the middle half of each edge with another diamond. So you can keep doing this ad infinitum. And well, when you equip these graphs with a shortest path metric, but scale down so the diameter of these spaces are always 1, then you can have an inverse limit. And that inverse limit space is Loxo space. And there's natural maps going down. Well, yeah, you need these maps to construct an inverse limit, but there's natural maps going down from one space to the previous one just by collapsing each of the diamonds onto the edge that they came from. So for example, the map from G0 to G1, these 2 points, it collapsed down to that point. And so in general, the map is going to be 2 to 1 in some places and 1 to 1 in other places. So a theorem from Schur and Kleiner in 2009 is that every Lipschitz map from Loxo space into a Banach space with the Radon-Nikodym property is differentiable almost everywhere with respect to the structure map pi0. So this pi0, when you collapse all of the edges one after another, you get a map all the way down from Loxo space all the way down to G0. And I guess I'm kind of abusing notation and also calling that pi0. But G0, this is a subset of R. This is an interval. So this is allowed to be a structure map. A structure map just has to be a Lipschitz map taking values into a finite dimensional Euclidean space. And this almost everywhere, I didn't tell you what the measure is, but I think it suffices to say that there's a probability measure on all of these spaces that push forward to one another, and such that the measure on G0 is just Lebesgue measure. And so what that means is that if you pick a generic point with respect to Lebesgue measure down here, and you look up and look at its fiber, probably it doesn't take too much imagination to see that this fiber, maybe I'll draw it like that, the fiber is going to be a Cantor set generically. So a Cantor set is a perfect set. Every point is an accumulation point of its fiber. And so almost every point is an accumulation point of its fiber, and at almost every point, the function is differentiable. So that means that the hypotheses of our observation won't apply. And so that means that Loxo space does not, by Lipschitz, embed into any Banach space with the Radon-Nikodym property. And there is also a different proof of the non-embeddability of Loxo space into RMP spaces by Ostrovsky. And actually his method of proof, I think, is a lot more direct and kind of more natural, and it just uses the martingale characterization of RMP. And maybe before going on, I'll just say a quick word about how you might prove this theorem. Well, just a very small part of the proof. So if you want to prove that your function is differentiable almost everywhere with respect to pi0, and pi0 is taking values in a one-dimensional space, then you just then to construct a derivative, you just need a single number at each point. So how do you do that? How do you come up with a candidate for your derivative? Well, this space G infinity, you can think of it as a quotient of a Cantor set crossed with an interval. So just for example, for G2, let's say I'll draw my axes like this. So this axis is going to be a Cantor set, and this axis is an interval. And so we can have a curve up here that maps down to this curve on G2. And then we can have another curve here, right, that maps down to the same thing, but it takes this bottom part right here. And then, well, okay, so then there's two more curves. Let's say you'll have a green one that goes down like that. And then there'll be a last curve, but I won't draw it in. And so that's a quotient from these four lines up to G2. So as you can imagine, if you pass to the limit, you can have a map from a Cantor set cross an interval down onto G infinity. And the measure on G infinity is actually such that if you take the natural measures on the Cantor set and the interval and take their product, then the measure on that set pushes forward to the measure on lossless space. So if you have a Lipschitz map from lossless space into an RNP space, then it'll restrict to a Lipschitz map on each one of these curves. And then just by definition of RNP, you have a derivative almost everywhere for those curves. And then you can do an averaging procedure to take those derivatives and then push them forward, and you'll get a well-defined function on lossless space itself, and that's your candidate for a derivative. So the idea is just that you have a sufficient family of curves that place together nicely with the measure on your space, and that's basically what's driving this theorem, that you can have a differentiation theorem. All right, next example, the Heisenberg group. So the Heisenberg group is a Lie group. As a smooth manifold, it's R3, but it's equipped with this non-abelian group product. And as a Lie group, it's isomorphic to upper unipotent 3x3 matrices. It's also a metric space. So how do we make it into a metric space? So we can equip it with a group norm, and then once you have a group norm, then you get an associated left invariant metric. So this one is the group norm. So notice this this kind of funny scaling. We have t squared here, but we have a raise it to the 1/4 power out here. So it's definitely not a vector space norm, but it will satisfy the triangle inequality with respect to the Heisenberg group product. So that there's your triangle inequality for a group norm. And so then once you have a group norm, of course, then this is the way that you associate to it a distance function that's left invariant. So left multiplication is an isometry of your space. Oops. Okay, so the important theorem for the Heisenberg group, there's a lot of names attached to it. So I'll explain why there's so many names in a minute after I explain the theorem. So the theorem says that anytime you have a Lipschitz map from the Heisenberg group into an RNP space, then the map is differentiable almost everywhere. And your structure map is the abelianization map. So in this case, the abelianization map just maps. It just drops the third coordinate, so it just projects onto the first two coordinates. So the t-axis is your commutator subgroup, and almost everywhere the measure is just a big measure in R3. And so then of course, since the fibers of this map are just the t-axis, every point is an accumulation point of its fiber. And so then by our observation, the Heisenberg group does not by Lipschitz embed into any RNP space. So about these names, so I think really this is Ponceau's theorem. So Ponceau proved kind of the original differentiation theorem, but I guess I haven't read Ponceau's original paper, but I guess he never made the observation that this implies non-embeddability results. So Sems in 96 observed that this implies that the Heisenberg group does not embed into any finite dimensional Euclidean space. And then independently, Chigger and Kleiner and Lee Nauer kind of observed that, well, actually it just works, the proof works verbatim if you just replace Euclidean space with RNP space. Okay, so now I'll just talk, just give a quick idea about why a differentiation theorem should be true. So what you're looking at here are translates of the xy plane around an R3 with respect to left multiplication by the Heisenberg group. So for example, if you take the x-axis, that guy, and you move it around using the isometries of the Heisenberg group, the left multiplication, this axis is going to start to shear. So for example, if you move it in the negative y direction, it's going to start to tilt like that. And if you move it the other way in the y direction, it's going to start to tilt the other way. So this tilting the axis is gaining well, it's moving in the z direction. So if you move it this way, it starts to tilt this way. And so if you do this, if you move the x-axis all the way around your space using left multiplication, what you get is a foliation of the Heisenberg group by lines. And you can also do this for the y-axis. So if you start off with the y-axis and you start to move it around using left multiplication, then it's going to start to tilt. So if you move it that way, it'll tilt this way. If you move it this way, it'll tilt this way. And so then if you do that, you'll get a different foliation by lines of the Heisenberg group. And so then that means that at every point in the Heisenberg group, you're going to have two lines going through it. One is a translate of the x-axis, one is a translate of the y-axis. And then so then you can just use those lines to form partial derivatives of any Lipschitz map into an RNP space. Because by definition, when you restrict the map to these lines, it's differentiable almost everywhere. And so then you piece together these derivatives along these partial derivatives along lines, and then you'll get a candidate for a derivative for your map into an RNP space, right? And you need two partial derivatives because the structure map takes values in a two-dimensional space. All right, so why does this have a chance of working? Like why should this derivative have a chance of actually having the required approximation properties? Like for example, what's the difference between doing this and then but trying to do the same thing if you used just Euclidean addition instead of the Heisenberg group product? You know, in Euclidean addition, if you take the xy plane, you start translating it around, right? It stays the same. It stays parallel the whole time. But in the Heisenberg group, because of this kind of twisting that's going on, it's possible for any 2 points in the Heisenberg group, you can connect them by a curve that is piecewise a translate of the x or the y axes. And so it's because of this kind of global connectivity by these translates of lines that are belonging originally to a two-dimensional space that's going to let you be able to end up proving your differentiation theorem. Okay, so now I'll come back and then talk about our question 1 again. So just an easy observation is that these differentiation methods, they not only rule out global embeddability into RNP spaces, but local embeddability. And the second thing is that these are essentially the only methods of which I'm aware that you can use to prove non-embeddability into RNP spaces. Well, maybe there's another way, maybe that the proof that I mentioned by Ostrovsky for Loxo space, but that uses martingale methods and it's similar, but you also cannot use those methods to rule out local embeddability. So that's the motivation for the question. So once you make these two observations, then I think this question kind of naturally pops out, is that whether it's true that local embeddability into RNP spaces actually implies global embeddability. And well, when you're thinking about trying to answer this question one, well, you need to have some, if you want to answer, you need to have some tools to prove some positive embeddability results into RMP spaces. And so when I started thinking about, how do you do this, kind of the best results that I could find are all have to do with Lipschitz free spaces. So the Lipschitz free spaces, these are Banach spaces into which your metric space canonically isometrically embeds. And well, they go by a lot of different names. They also go by Aaron-Zeal spaces, or in Mikhail Ostrovsky's talk, transportation cost spaces. I'll define them properly on the next slide. But for now, you just need to know that they're useful for embedability. And so here's a list of spaces that I could collect that a list of metric spaces whose Lipschitz free space is known to have the RMP. So I don't claim that this list is exhaustive, but these are just the ones I could collect. And if anybody knows any space that fits onto this list and is not part of the ones already there, I'd be happy to hear about it. So uniformly discrete spaces, their Lipschitz free space has RMP. Uniformly discrete means that all non-zero distances are bounded below by some positive constant. Also snowflakes of separable dual Banach spaces. So snowflake means if you have a metric, say D, and then if you raise it to a power alpha, where alpha is between 0 and 1, this will still satisfy the triangle inequality. So this gives you a new metric, and it's known as the snowflake of the original metric space. So also metric spaces are proper uncountable, ultrametric, and length 0 subsets of R trees. So in each of these things, the authors prove something stronger. They didn't just prove that these spaces had the RMP, but whatever they prove, that it implies RMP. Okay, so then once you start thinking about this question one in relationship to Lipschitz free spaces, then you realize that actually that there's a natural analog, and that, well, the question is, if the Lipschitz free space of your metric space has, over every compact subset of your metric space has RMP, then is the same true for the total space. And so then I decided to work on this problem because, well, it looks like it might be more tractable than the first problem. Okay, so before we talk more about question two, I'll just go ahead and do a quick review of Lipschitz free spaces. So suppose that we have a metric point with base point 0. Then the Lipschitz free space over X is the closed span of the pointwise evaluation functionals in the dual space of real valued Lipschitz functions that vanish at the base point. So I should say these are real valued, or valued Lipschitz functions. And the norm, of course, is the Lipschitz constant of your function. So there's many other characterizations, but this will be the one most relevant for this talk. And some quick facts is that the mapping P maps towards pointwise evaluation function lets an isometric embedding of your space into this Banach space. The dual space, or the Lipschitz free space, is lib 0 of X, the Lipschitz functions that vanish at the base point. And so actually this inclusion LF of X, including into the dual space, that's just the double dual embedding. And the weak start topology on the ball of the Lipschitz functions is the topology of pointwise convergence. And whenever you have a subset of your metric space, then its Lipschitz free space kind of canonically and isometrically is a subspace of the total space. So the proof of that is just essentially the McShane extension theorem, which says that real valued Lipschitz functions can always be extended from a subset to the whole space without increasing the Lipschitz norm. All right, now we'll get back to question two. That was the question about whether the Radon-Nikodym property is kind of compactly determined for Lipschitz free spaces. And well, we'll see actually that although I couldn't answer this question, it turns out that it's easier if you replace RMP with the approximation property or the Schur property. So quick review, the approximation property of a Banach space says that the bounded operators on your space are well, it's exactly equal to the closure of the finite rank operators with respect to the topology of uniform convergence on compacta. And the Schur property says that weakly null sequences are also norm null. And so here's the theorem again. Assuming that your space is complete and locally compact, then the Lipschitz free space has either the approximation of the Schur property if the Lipschitz free space over every compact subset has that same property. And just to mention one possible corollary that you can get using this, just to see how it kind of plays together with existing results, is that the Lipschitz free space over every connected complete Riemannian manifold has the approximation property. And so the proof is pretty automatic. You just use the previous theorem. So you just need to check that the same thing is true for every compact subset. And then you use a result of Lancienne and Perneka, that the Lipschitz free space over every doubling metric space has the Radon-Nikodym property, or sorry, has the approximation property. So doubling, metric space being doubling means that there's some constant n depending only on your space, so that any ball of radius r centered at any point can be covered by n many balls of half the radius. And so I guess you also just need to know that any compact subset of a Riemannian manifold is doubling, and then you kind of get this theorem. All right, so now I'll start to try to discuss the proof of that theorem. And so the first step is to kind of take a closer look at what local compactness means for a metric space. Okay, so here's our settings. We have a complete metric space, and we have a downward closed collection of closed subsets of X. So downward closed means that if A is a subset of B and B is in your collection, then also A is in the collection, and A is closed. Let's assume that all of the sets that we're talking about are closed, and also excuse me, the collection should be non-empty. So the empty set should belong to your collection. So that's what downward closed means. So if you want to just keep in mind the example of the compacts, then that's fine. Throughout this whole discussion, you can, well, that's not necessarily true. Okay, so the compact's an example, but we do need to talk about downward closed collections in generality. Okay, so a definition, we say that a closed subset, so this F is closed, is locally modeled on your downward closed collection if for every point there exists a theta, so that the ball in F, the ball in F relative to F is belongs to the collection. So if D are the compacts, then this is exactly saying that your subset is locally compact. A stronger notion is your subset being uniformly locally modeled on this collection. So this condition that I've written down is stronger in two ways. So the first way is that we flip the order of quantification. So it's the same theta that's working for any point. And the second thing is that we're not only requiring that F intersected with every ball belongs to your set, but any finite union of balls. So if your set D is an ideal, so if D is an ideal, meaning right, A and B in D implies that their union is in D, like such is the case for compact sets, then you don't need to do this finite union thing. You can just talk about one ball, because as soon as each ball is in it, then by the ideal property, then all finite unions would be in it. But for a general downward closed collection, we do need to talk about it. Unfortunately, we need to use the stronger condition. All right, so those are two definitions. And well, here's another definition. We want to talk about all of the possible sets that are uniformly locally modeled on D or just locally modeled on D. So Lm of D, that means all of the closed subsets that are locally modeled on D, and ULM of D means all of the closed subsets that are uniformly locally modeled on D. So you should think of ULM of D and Lm of D as operators that you can apply to your collection, and then you get some larger collection. And just a couple observations. the LM operation is idempotent. So if you take LM twice, you get the same thing, right? So that's kind of just saying that the relation of being locally modeled is transitive, but that's not true for uniform local modeling. It's not transitive. So just a quick example: if you take D to be your finite subsets, so say that's your downward closed collection, and you look at the following metric space. So suppose that you have an infinite metric space, and all the distances between points are either a 0 or a 1. So you can imagine you know, some scaled version of the unit vector basis in any LP space. So take that metric space, an infinite 0, 1 metric space, and then take a copy of it. Oops, I didn't want that there. So take a copy of it and then scale it down. And then take another copy. And I didn't get rid of that D. All right. And scale it down again. All right, and keep doing this, and take a sequence of scales. The scaling parameter is going to 0. So then if you take any finite piece and you define a metric space so that the distance between any two of these copies is, say, 2. Then if you take any finite piece, that will be uniformly locally modeled on D. But on the other hand, the entire space is not. So the total space is not in here. So then once you know that, then that kind of implies that the that the total space does belong to doing ULM twice. Okay, so when you take ULM twice, you can get a strictly larger collection of sets. Okay, so then if you can get something larger, what happens if you keep iterating that? So you take ULM, take ULM, take ULM over and over again, say transfinitely many times. What kind of collection of sets can you get? So let's kind of define this properly, what this means to do this over and over again. So like, what is the kind of collection of sets generated by D under ULM? So define a downward closed collection to be ULM closed if it's closed under this operation. So when you take it, you get the same thing. And then the ULM closure of a downward closed collection is just the smallest ULM closed downward closed collection containing D. This is the standard procedure to talk about, you know, a collection of sets generated by a collection of sets with respect to some operation. All right, so then once we have everything set up this way, then we can write down 2 lemmas that are going to imply our theorem.
Excuse me.
So the first lemma is, yes.
This locally modeled is, you also call it small scaled extension, correct?
Exactly. I figured when I was writing this talk that this was more descriptive language.
Yes.
So I'll change the paper.
No, thank you.
Yeah, thanks. Right. So the first lemma is that if the original downward closed collection you start off with is actually an ideal, then when you take the ULM closure, then you actually get all of the sets that are locally modeled on I. So maybe I should go back. Maybe I should go back here and say something. So what's an example of a collection of sets that's ULM closed? Well, LM of any collection is ULM closed. All right. If you have all of the collection of sets that are already locally modeled on something, then if you take anything further, then it's already going to be locally modeled. Right? That just comes down to what we already said right here. So, so one containment here is easy. The ULM closure of I is automatically contained in here. So the content of this lemma is going the other way around, that actually these 2 things are equal. And the second lemma is that if we assume our space is bounded, and we define two downward closed collections. The first one is all of the closed subsets, so that if you look at an operator that is taking values in the Lipschitz free space of that closed subset, then that operator is approximable by finite rank operators. So this set is going to, obviously it has to do with the approximation property, and the statement that that your space, that your Lipschitz free space has the approximation property is exactly the statement that X belongs to D1. And then we define another set D2, which is, okay, all of the closed sets, so that Lipschitz free space over that set has the Schur property. So then X belonging to D2 is the statement that, that Aleph of X has the Schur property. So then once you have those, so then the content of the lemma is, the statement is that these sets are ULM closed. So then once you have these two things, they immediately apply theorem 1, actually. So I mean, it's, there's only one way to prove it, of course, but I'll go ahead and write it out. So actually, first you need a reduction. A result of Colton in 04 lets you reduce to the case where X is bounded. So Colton proved that, he proved something stronger, but it implies that if every bounded subset of your space, if the Lipschitz free space over that has an approximation property or Schur property, and the same thing is true for the whole space. And okay, so the assumption that that Aleph of A has the approximation property for every A near ideal is kind of exactly translates to I being a subset of this collection D1. And then saying that Aleph of A has the Schur property for every A in the ideal is saying that I is a subset of D2. Okay, so then X is locally modeled on I by assumption. Right, I guess I should say I haven't stated, so the previous versions of this theorem that I was stating, I was just the ideal of compacts. So actually something more general is true. If you replace compacts by any ideal, then you get the same theorem. So by assumption X is locally modeled on your ideal I. By the lemma, this is equal to the ULM closure of I. And well, by lemma 2, these sets are ULM closed, and I is a subset of one or the other, depending on what you're assuming. And so just by definition of ULM closure, then I is contained in these sets. And that's if I is contained in D1, that's exactly the statement that you have approximation property. Or sorry, if X is contained in D1, that's exactly the statement that you have the approximation property, and X being contained in D2 is saying that you have the Schur property. Okay, so maybe I have only a few minutes left, 5 minutes or so. So let's see. Maybe I'll quickly try to talk through words and for how you might try to prove this first lemma. So actually, the second lemma is if you've worked with Lipschitz free spaces at all, then it's completely standard for how to do it. So for the first lemma, so how do you do this? So if you the way to prove it, yeah, I'll go ahead and just jump to this one, right? So how do you prove this? I'll just try to go through it quickly. So like I said, the ULM closure contained an LM of I, it's contained in LM of I, that one's automatic. So to prove the other way around, what you're going to do is show that if F does not belong to the ULM closure.
Chris, do you want to make it full screen?
Actually, this app, let's see. So if I do this,
yeah,
I think this view is better. Yeah.
Oh, sure. Okay.
Yeah. So if right, so if F is not in the ULM closure of I, you'll show that this implies that F is not locally modeled on I. So how do you do this? I guess I'll just talk through it really quickly. If you assume that F is not in the ULM closure, what you show is that, so this implies that for any theta, then you can find a ball so that the ball of that radius intersected with F is also not in the ULM closure. of I. So you kind of just use the definition. And so then if you keep repeating this over and over again, you can keep taking f and you can intersect it with balls whose diameter is going to 0. And so then by completeness of your space, this is going to converge to a point. And the fact that none of these things belong to the ULM closure of I implies that they don't, in particular, they don't belong to I. So then when you intersect all these things, you get a single point, and then this point can have no neighborhood that belongs to I. So then that means the set cannot be locally modeled on I because you have this bad point that has no neighborhood that belongs to I. Okay. And I was going to talk about lemma 2, but I don't think there's time. I'll go ahead and mention the kind of partial results that I have for RNP. So let's assume that your metric space is countable and discrete. So discreteness is a particular kind of local compactness, but I guess it's a pretty strong assumption. Then we're going to recursively define a sequence of ideals. So we'll define find 0 to be the ideal of finite subsets of X. And then find n is just defined recursively by taking the n plus 1 is defined by taking all the sets that are uniformly locally modeled on find n. Right, so as we talked about before in the previous slide, if you were to apply this ULM procedure transfinitely many times, then you will actually pick up the entire space. So but if you only do it finitely many times, then you might not get the entire space. And then we'll define lib0 of nx to be a subspace of lib0 of x as those functions that are supported in this ideal, find n. So the fact that this is an ideal tells you that this collection is a subspace. It's not a closed subspace, but that's okay. And then analogously, you define the Lipschitz free space n comma x to be defined the same way as usual, but instead of using all of the Lipschitz functions, you just look at the Lipschitz functions that are supported in this ideal. So then here is the kind of the main result, that your starting point, Lipschitz LF of 0 comma x is a separable dual space, and it thus has the Radon-Nikodym property. And then there is a kind of a natural restriction map from LF of n plus 1 down to LF of n, and that's a semi-embedding. So semi-embedding means that the operator is it's bounded, it's injective, and the image of the ball is closed. The image of the unit ball in your Banach space is closed. And so just the important thing to know is that that the semi-embeddings of separable metric spaces into RNP spaces preserves RNP. So by induction, then all of these spaces have RNP. And then just a corollary is, okay, well, if your metric space happens to belong to one of these ideals, then its Lipschitz free space has RNP because it's just equal to LF of n of that space. And okay, it looks like we're ending right on time. So thank you for your attention.
All right, thank you so much, Chris, for a very nice talk. All right, so we can open for questions now. If you have any questions, please go ahead.
Yes, I have one question for Chris. Thank you for this nice lecture first. This is Gilles Godefroy speaking from Paris. If you replace approximation property by bounded approximation property in your theorem 1, maybe assuming some uniformity on your compact sets, can you get a conclusion? Can you get something?
No, I don't think so. Yeah, somehow this method, right? So the reason why this works. So here's the lemma. The reason why you get that these sets are ULM closed, it comes down to the fact that convergence, UCC convergence comes from a topology, right? So it's kind of transitive. The UCC closure of something is is itself closed. So you know, for BAP, you can't do that iteration process. So no, I don't think so. I don't think so. All of these properties, and even if you go back to the results of the other paper that I mentioned at the beginning, and they also had weak sequential completeness and L1 saturation and whatnot. These are all isomorphic properties, but they're kind of not quantitative, and there's no constants involved like you have for BAP. So I don't think that you can prove anything too quantitative with these methods. But if any of the authors of that paper think differently, then they can feel free to say so.
Okay. Well, I was afraid of that answer, of course, but I find it very natural. What is behind my question is this famous problem, which goes back to Carlton's paper in 2004, whether when you take a uniformly separated metric space, is it so that the free space has a bounded approximation property? This is open and certainly important. Okay, thank you very much. Thank you.
Thank you.
Thank you so much, Jill. Any other questions or comments?
One question.
That's a very hard problem, I have to say. For Jill.
Okay. Jill, you're on mute, so we didn't hear what you said. Okay, but I think you agreed that. Okay.
I have a question. Can I ask a question?
Sure, go ahead, Tony. Okay.
Yes. Okay. So my question was for these small-scale closures. You call them somehow differently right now, but is there any topology behind them? Is there some topology on a family of set, which because you definitely treat them as such?
Right. No, I haven't thought about it, but I don't know. Mm-hmm. Yeah, I guess I haven't thought about it. I mean, it seems plausible. Yeah, it seems plausible.
I mean, your proof of lemma 1, or it is theorem 3.4 in your preprint, right? It really reminds the proof of bare category theorem at some level. So I was thinking maybe.
Yeah. You're right.
It's really nice. It's really nice. This whole.
Okay, thank you. Yeah, maybe I'll think about it for topology, and there's still a lot of work to be done on the paper. So maybe if there's something interesting, maybe I'll include it. So thanks for pointing that out.
One question. To satisfy Lipschitz condition is the same to have limited norm.
Sorry, can you ask your question again?
If function satisfy Lipschitz condition is the same that function is have limited norm.
Limited what?
No, you assume function satisfy Lipschitz condition. So it means that differential on the image less than differential of original. It is some constant. So this is L capital is the same as norm of the function f.
Oh yes, it is. It's the smallest L. The smallest L is the norm of the function.
I see.
Okay, thank you. Any other questions? If not,
can I ask a question?
Yeah, go ahead. Okay.
So I'm trying to understand Radon-Nikodym property. I'm from the forest. I don't know much. So suppose that you have like a Wasserstein one space or Lipschitz free space. I guess this is the same thing over just standard plane. Does it have Radon-Nikodym property or not?
Oh, over the plane, you said?
Yeah.
Oh yeah. I didn't mention that. So that's a natural space to look at. So if you just look at the line, just the real line, it's Lipschitz free space is big L1.
Yeah.
And big L1 doesn't, right? So, but the line of course is a subset of the plane. So then that means that L1 is a subspace of the Lipschitz free space over the plane. And so since there's so it doesn't.
Okay, thank you. Yeah. But I also looking at your paper. So at the end of the first section, you write some examples, and of RNP spaces, or actually of spaces which Lipschitz-free spaces are RNP, and then the third point are proper spaces or separable dual Banach spaces distorted by some stuff.
Yeah.
And the plane doesn't satisfy this third condition.
The plane? The
Yeah,
plane does not, correct.
I can see. So it's not separable dual Banach space, or
no, it's because you need to do the snowflaking, or do the gauge.
Okay, so this, yeah, I got it. So this distortion cannot be trivial. Yeah, I see.
Yeah. So what happens when you snowflake is that you lose all rectifiable curves. When you snowflake a space, then there's no rectifiable curves at all anymore.
Gotcha.
No finite length curves.
Thank you very much. Very nice talk.
Okay.
Thank you.
Thank you from me too. And I have a perhaps completely silly question, if I may. I've never thought about these things before. You required your metric space to be complete.
Yes.
Just a matter of convenience, or is there some way that if you know something about a non-complete space, you can't just...
No, yeah, that's a good question. Yeah, I should have said something about that. I guess I ran out of time. I didn't say things that I should have said. So if you don't assume completeness, then you're assuming nothing at all, because every metric space belongs to the completion of a discrete space. Right? So for example, if you take any metric space X, you can just look at X crossed with an interval, and then you can look at some kind of discrete approximation to X that gets finer and finer as you go down. And so, so X will belong to the completion of a discrete space. And these Lipschitz free spaces, they only did the Lipschitz free space of a metric space is the same as the Lipschitz free space of its completion. And the same story is true for embeddings, so completion of discrete space. So, so if you don't assume completeness, then yeah, you really assumed nothing.
Thank you. And thank you for the talk, of course.
Thank you.
Thank you very much, Chris. I suppose that's all we have today. So thanks again, everybody. So I'm going to stop recording.